Okay, welcome to one more video on triple five timer applications. So in this particular video we will see the monostable multivibrator. Okay, this is a circuit diagram of a monostable multivibrator using triple five timer, and the pulse width of the quasi-stable state is given by 1.1 RT into CT, provided the higher threshold voltage of this triple five timer is 2/3 of VCC, which is nothing but the control voltage is 2/3 VCC. So we know that uh, if we are applying a beat trigger, so let me just write the if this is the trigger signal, which is VCC initially, and then if it goes to a value which is 0, and then if it again goes up here, and suppose if this is the type of trigger signal what you are applied, where this is 0 volt, and let me also indicate the line corresponding to VTL, and we will write what is the expected output waveform. So we know that output remains in the in the stable state till you apply the trigger signal. Now this is stable state. So since the trigger signal is going below VTL, so it goes to quasi-stable state, which is nothing but, of course, this is, we are talking about the output voltage, and this is 0, and here it is the stable state. Here this is VCC. This is a temporary state. It remains in this high state till a time of TPW, which is decided by the values of CT and RT, and it again comes back to, okay, this is now VCC, this is a quasi state, which is a temporary state, and it will again come back to stable state of 0, and it will again go back to quasi stable state upon giving the next trigger signal. A trigger signal is one where the voltage level has to go below VTL. So this is what we are expected. So let us do the simulation of the same. I have already rigged up the circuit here. You can see this is RT is taken as 10 kilo ohm. This is 0.1. I have rigged up the circuit as per the expected things. Let me apply a trigger signal. So I just left it open so that we can properly. Okay, maybe we'll just go back here and then try to find out, okay, what should be the time period of the signals. So let us assume that since I've taken the RT as 10 kilo ohm and this as 0.1 microfarad, so I have to get, okay, this is 0.1, okay, this will become 1.1 millisecond. So for those R and C values, I have to get it as 1.1 millisecond. So this is 1.1 millisecond. Since it is 1.1 millisecond, let me take the period of this more than this. Let me take it as 3 millisecond. Let me take this time as hardly maybe 0.1 millisecond. So I have to apply a trigger signal whose overall time is 3 millisecond, whereas its off time is hardly 0.1 millisecond. So then on time has to be 2.9 millisecond, and it has to have a minimum of 0, and then it should have a maximum of VCC. Let me go back to this schematic and then take a source now. So this is my source. Let me take the source. Okay, let me edit the parameters. Okay, I'm just connecting that trigger signal to pin number 2, and then let me go to advanced. So this is a pulse initial value. Let me take it as, okay, let me take it as 0, and take it as 5. The delay, let me make it as 0. The rise time, make it as simply 1 microfarad. The fall time also 1 microfarad, and the on time, let us take it as 2.9 millisecond, and total time is 3 millisecond. And okay, let us have a number of cycles. Okay, this is the setup. Now let me run. Okay, let me just specify the timings. So since there is a 3 millisecond one, let me just do it for 10 milliseconds so that I can see at least 3 waveforms. Start from 0 with a time step of 1 microsecond. Okay, I'm done. Let me see the trigger signal now I have. You can see now this is the trigger signal. It is initially high here. It goes down to 0. This is for hardly 0.1 millisecond. It's again, can you see this is almost tallying with this type of graph, okay, waveform that I had. Okay, this is what I want. Okay, I'm getting almost similar to that. Let me see what is the output waveform here. This is my output. Let me just put it on a different pane so that you can make out. Let me just put this over here. Now you can carefully observe. So when the input voltage is okay, when the input voltage is VCC, you can see the output voltage is 0 here. Okay, forget about this initial state. This is 0 now. So once the trigger signal goes to 0 volt, that is less than VTL, the output is going to high, and it is remaining in high for a predefined time, which is equal to 1.1 millisecond as per our calculation. You can actually measure what is the time. What I can do is I can use the cursors and place it at two extreme points of my pulse width, and if you see the difference, it's almost, you can see this is 1.1 millisecond. That's what is expected from this. Okay, this is what is expected, and this is true because your capacitor voltage is actually changing from, okay, when it goes to quasi-stable state, capacitor voltage charges towards VCC. Whenever it comes to VTH, output voltage goes down. You can actually see that also. So what I'll do is I'll just plot the capacitor voltage also. Fine. Now you can see this is how the capacitor is charging. Capacitor charges. Now you can see whenever it reaches VTH, it is coming down. You can see now this is your charging time. You can see discharge time is very quick. Of course, if you zoom it, you can see, if you zoom in, you can see there is some time taken, which is very small compared to the pulse width. So that's why we say almost a vertical line coming down to ground from VTH. So exactly this is how we usually write the capacitor voltage. We actually write the capacitor voltage is 0, it goes to VTH, and then it comes immediately to 0. So this discharge time is almost instantaneously 0. And of course, let us try to see if I don't make my threshold voltage to go below less than VTH, what happens. So what I'll do is I'll go back here, and let me just introduce, okay, let me just go to this waveform. Let me have an initial voltage of we take it as 3 volts. Okay, let us see what the difference. Okay, let me just run it. Now if you can see here, carefully observe this. Initial voltage is 3 and it is going to 5. So the input, you have a trigger signal which is varying from 3 to 5. 3 to 5. If you actually see the output voltage is not at all making any, it is always in the stable state of 0. It's not going to quasi stable state because the voltage of your trigger is, even when it is 0, it's actually 3 volt. Can you see here? Can you see this is 3 volt? Why it is 3 volt means, okay, in my simulation I have specified the initial voltage as 3. Even if I make the initial voltage as maybe 2, still also it won't work. Because the VTL for this particular case is 1.66. So if I run it now, you can see now it is 3. I have modified it to 2. Now if I run, this becomes 2. Can you see now this is 2? Can you see now this is 2? It's still not, this is going only up to 2. This is output is still there at stable state. So when does the output goes to quasi stable state? If this voltage is going less than 1.66. So let me just make it as 1.5 and see the change in my plot. So what I'll make is I'll make the initial voltage as 1.5. Since this 1.5 is less than VTL, I have to get the proper waveform. So now it is modified. I'll save this and then, okay, it's fine. It's not saving in C drive. Now you can see you're getting it. See now? Since the input voltage has gone below 1.66, which we made it as 1.5 as my low voltage, now output is going to quasi stable state. Now it's remaining in state of 1 for a predefined time of 1.1 millisecond in this particular case. So this is what is so important in case of a trigger signal. A trigger signal is one where the input voltage has, that's why this dotted line is so important. The trigger signal has to go below VTL. So what I'll do is next we shall change this control voltage. Instead of having a capacitor which is fixed here, let me just put a sine wave here, or maybe a DC voltage. So if I put a DC voltage there, let us see what happens, how the pulse width changes. So what I'll do is let me just take out this and then put a battery. So what I'll do is I'll use a battery. So this is a battery. Let me just use this. Okay. Just a minute. I'll place this battery here. Let me make the voltage as maybe 4 volts. Now you can see this is 4. Actually, when I actually put the capacitor here, the control voltage was 2/3 of VCC, that is 2/3 of I, which was 3.33 volts. So since now I made it exactly equal to 4 volts here, now the pulse width is not equal to 1.1 RTCT, it will be different. If you actually run it and see, the pulse width will be certainly more than 1.1 millisecond. You can see now, if you actually measure that pulse width, which is this, if you see the state exactly when it is high, you can see this is one, this is the other one, this will be certainly more than 1 point. Can you see it is now 1.62 millisecond? 1.62 millisecond. Let us try to verify whether this is theoretically correct or not. So let us try to find the expression for the pulse width when you have a trigger, when you have a threshold voltage other than 2/3 VC. Assume that you have a V reference. When you have a V reference, we know that this is a control voltage, sorry, capacitor voltage expression. VC is equal to V final minus V initial e power minus T by RC. So the capacitor voltage will be equal to VTH, which is in this case V external or V reference is equal to V final is VCC minus V final again VCC, V initial is 0, this is e power minus T pulse width by RT CT. Suppose we actually look for this expression, if you solve for this, so then TPW will become RT CT ln of VCC divided by VCC minus V reference or V external. V reference or V external. Now in this case, in this particular example, we take this as 4 volt, then this becomes RT CT into ln of 5 by, okay, this is now 4, sorry, this is 5 minus 4, this will become 1, so it is ln of 5. So we can actually verify what is the value, what we actually got the pulse width as 1.6 millisecond. You can see this was 1.61 millisecond. Let us see what is the value that we're going to get here. So R is 10 exponential 3 into 0.1 exponential minus 6 into ln of 5. You can see now it is 1.609 millisecond. So this is my TPW. It is not okay. If you put a capacitor here, this becomes 1.1 millisecond. Since you have a external reference voltage which is applied, the pulse width is now decided by this voltage along with RTCT. This voltage along with RTCT. So what I'll do is I'll go back here and exactly measure what is the time. If you can zoom it and then measure it here. Okay, I can just slightly bring this closer. You can see now it is almost there as our expected value. It is 1.609. So it is, that's what we expected here. This was 1.609. So this is the value that is measured using simulation. So this way we can able to change the pulse width of the monostable multivibrator by using three ways. So what are those three ways? One is external voltage, other one is RT/CT. Of course, you can put a sine wave here, as the sine wave has got different amplitudes. So depending on the amplitude, you will going to get the width of the pulse is keep on changing. So that you can certainly do it. Of course, you can change the value of this RT/CT so that the pulse width again changes. That you can verify when you're doing the simulation. So let me just show you what happens if I replace it by sine wave. So I'll just take out this, then have a copy of this over here, but I'll modify this source by a sine wave with some offset. Maybe let me take the offset as around 3 volts. Let me give an amplitude around 2 volts. Let me have a frequency of around 50 hertz. 50 hertz. This is fine. Okay, this is done. If I run it now, same. Okay. If I run, what's happening? Oh, sorry. Yeah. So if you want to see this width variation, what I have to do now is I need to apply. Okay, let me just see it for more time. So only thing is that this time has to be modified so that you can able to see it more effectively. Let me just make this around 100 milliseconds so that you can see 10 cycles. Can you see this width is keep changing? Let me compare that with your sine wave. You can see this is my sine wave. Let me just take out all these things so that what I'll do is let me remove this. Cancel. You can see now as your input amplitude is increasing, so width is more. Of course, the width is reduced here during negative half. You're not getting any pulses here because why you're not getting any pulses here means the input voltage is so less, but this has not gone below VTL. So what I'll do is I'll apply a trigger signal which is going from 0 to 5 instead of 1.5 to 5. So I'll just go back here. So you can see here this I made it 1.5. Let me make this 0. If I run it now, you can see you're not getting the pulses during this period because your trigger signal, the input voltage is VTH is here, and your control voltage or your trigger signal is always more than VTL. Suppose if I start from 0, now you will get it for each and every. See now? Can you able to see the pulses for the entire variation? You can see the pulse is the least here, the pulse is the maximum here. The width is maximum here because your control voltage is there at the peak. The width is minimum here because the control voltage is the least, because now the pulse width is decided by this V reference. Now V reference, we made a sine wave. When the V reference is at the positive peak, this width is too much, and when this is at the least value, then the pulse width is least. So that's how you can able to see the variation of the pulse width. So we can also see one more application of a 555 timer, that is bistable multivibrator. So what I'll do is I'll just go quickly and rig up a bistable multivibrator, and okay, what I'll do is let me just copy paste this, save as, okay, some bistable, okay, this has been saved. What I'll do is let me just come back to this. Yeah, okay, now we will see this circuit now. So this is a bistable multivibrator in which the input is applied to the both threshold as well as the trigger signal. So you're comparing the input voltage with VTH and VTL, and if the input voltage exceeds VTH, output goes down to 0, and if input voltage tries to go below VTL, output again goes to high. So what is this VTH VTL? Because you have a particular capacitor is connected to this control voltage, so this VTH is equal to 2 by 3 VCC, and then VTL is equal to 1 by 3 VCC. So when I say for this, it will be 3.33 volt, and whereas this will be 1.66 volts. So these are the voltage levels. Suppose if I apply input voltage which is already DC shifted, and if it is something like this, so what I'm trying to do here is I'm shifting it by 2 volt, and over and above this I'll apply 2 volt here. So this is, from here it is 2 volt, from here it will again come to 2 volts, so that it will touch 0 here. So you have this VTL, you have this VTH, which is 1.66 and 3.33. So whenever the input voltage exceeds 3.33, output will come down. So output will come down here, and whenever it tries to go below VTL, it again goes high. So when it will again come, so it will again come down here. So this will be there. This is the type of waveform we're going to get. So this is V0, this is Vin with respect to time, this is again with respect to time. So let us do the simulation here. See, now this is what I have in the simulation. This is a circuit diagram. So I have my trigger, and threshold voltage is shorted and given to a sine wave whose offset is 2 volt and amplitude is 2 volt, so that output will swing from 4 to 0. And okay, since I don't want to change the VTH VTL from 2/3 VCC and 1/3 VCC, I'm putting a capacitor here. So let me just run it here now. If I run it, you can see this is a sine wave. Okay, let me just take out this another waveform, whatever you have out here. Let me take out this is not required. Now if you carefully observe, whenever the input voltage tries to go below 2/3 VCC, somewhere here, maybe let me just trace this. So whenever it is, let me just trace it here. So this is almost 3.33. Can you see before 3.33 the output voltage is let me just have a look at the output voltage also. Can you see the output voltage is this is output voltage. You can see output voltage almost VCC when the input is less than 2/3 VCC. When the input exceeds, now the input is more than 2/3 VCC, which is now 3.6. So what is the corresponding output at that point? The corresponding, if you can zoom it out and then see here, this is your input voltage. Can you see the output? Output voltage is 0. So output voltage is 0. You can see it's almost microvolts. So when does again output goes to high? The output again goes to high when the input voltage crosses VTL. So VTL is this, so which is 1.66. Can you see somewhere here it is 1.66. At this point output is making a transition from 0 to 1. So this you can carefully notice here. Let me just zoom this and see. Whenever the input voltage is going down, whenever it goes down below 1/3 VCC, that is 1.66, output is going from 0 to 1. Can you make out this? This is 0 here and it goes to 1 when the input voltage is crossing 1.66, that is VTL. We can actually change this VTL VTH. Of course you cannot change, because in this simplified timer we know that VTL is always half of VTH, so you cannot change that VTL VTH condition or the relation. But what you can do is you can simply change the VTH value, so VTL will be naturally half of that. So what I can do is I can just replace this capacitor by reference voltage. So what I'll do is I will put a reference voltage here. I'll put a battery of, if you make a battery of hardly 1 volt, then VTH is 1, VTL is 0.5. For whenever your input voltage tries to go above 1, output voltage becomes 0, and if it goes below 0.5, it goes to high state. So you can run this and see. Can you see here? This is less than 1, it's going here. Okay, let us trace it and try to find out what happens here. Can you see input voltage is going down here whenever it tries to go below 0.5? Can you see this is 0.5 somewhere. When it is going less than 0.5, it goes to high state. This is there in high state as long as the input is lesser than VTH. VTH is 1 volt. So you can actually move this and see here. See now, whenever it is more than this, you can see this is whenever it is. Okay, what I'll do is I'll just make sure that. So where is this? Okay, just a minute. I'll move the wave over here, and this is also here. Now what is the voltage? The output voltage is high. Output voltage is high, and you can see okay, let me just move on one of them. So what is the input? Input is less than 1. Can you see input is how much? Input is hardly millivolts. Output voltage is high. Whenever this input voltage, this is my input voltage 1, if I move it above 1 volt, I can see 1.2. At that corresponding point, if you can see here, at this corresponding point the output voltage is 0. Just put the output voltage here and then see output voltage is 0 here. So when the input is more than VTH, the output voltage is 0. So what is VTH? In my circuit I have made the VTH as 1 volt using this. How did I made it 1 volt? Because this is 1. If you make this equal to 4, you will get it as per that. Suppose if I run it now, if the input voltage exceeds 4, output comes down to. Now it is looking between 4 and 2. If you can carefully notice, the output voltage is not at all having any transition because the output is not exceeding 4 at all. If you just see here, what the type of waveform you have? The waveform is swinging from 2 to 0. It's not going above 4 at all. It's not going above 4. Since it is not going above 4, output is not coming down to 0. So how do I make the output to go down from VCC to 0? I need to make the input voltage to go more than 4. So what I'll do is let me again shift it slightly more. Let me make it 2.1. If I make it 2.1, then it goes up to 4.1, then it will certainly have a transition. As you know, this has gone, whenever it goes above 4, it's having a transition. Okay, let me change the color of this. You can see whenever it goes more than 4, that is, since it's going up to 4.1, you can see whenever it crosses 4, it's going down to 0. Whenever it goes less than 2.05, the output goes to high state. Okay, this is how you can able to see. This is the bistable multivibrator. Actually, we have seen in this particular video both monostable multivibrator as well as the bistable multivibrator. In the previous video, we've actually seen the astable multivibrator. Okay, thank you.